All right, welcome everyone. So we're going to continue from where we left off, and then this is the part two of the Aspen um, palm kernel shell gasification. All right, so we are going to continue from where we stopped. All right, and then just a little recap. From the last video, we were able to set up the properties of this particular simulation, where we selected the component, the fluid package, and then we specify the NC to make it um, to help us to be able to analyze approximate and ultimate analysis, also software analysis for the PSK and then the ash. Remember, the PSK and the ash are both non-conventional, and then our carbon is the solid. All right, so after doing that, we went, this is your NC properties. All right, so approximate, ultimate, and then solve for. Remember, make use of the whole cogen, H cogen, and then D cogen. So coming down to the simulation, we set up the stream for the PKS, and then we set up our yield reactor. So let me just put this as yield, okay. And then we have the boiler, and then after we try to put in elemental phase first before we continue, and then for the water, we boiled it, then we did the superheating to 400 Celsius, and then we are moving on. All right, so moving on to what we have. Okay, so we're about to go to the R Gibbs reactor and then continue the process. So let's get to it. All right, so okay, so the R Gibbs reactor was used. Continue, we're going to continue from here. The R Gibbs reactor was used to perform the decomposition of the gasification of the palm kernel shell, with the assumption that this reaction follows the R with the Gibbs free energy minimization calculation. So that's basically what we are using to solve this forward. So before we get there, we have to split this steam. All right, we're splitting this steam, so I'm going to make use of the F split for it. So let me, yeah, I'm going to split it up. All right, because we are going to be having two Gibbs reactors, so we're just going to serve like a heating source for it. All right, so then to do this, let's just split them into equal halves. All right, so also we're also going to be splitting this. All right, we'll be splitting this. Okay, let me move. Okay, and then before I take this to the R Gibbs, we can just split it up into, okay, I think S6 is at the top, so let's specify for S7. So let's say we want majority of the product from the yield reactor to be going to the R Gibbs, because we're making use of two R Gibbs reactor actually. And then the idea of this, let's just say we are not trying to overload one particular reactor. So let's just put this here, and then okay, then we need our products. So remember, we have to remove ash from this, but we can send everything though. That's let's do this. Just have one product. All right, one product coming out. Yeah, let's check. Oops, sorry. Okay, let's check our. All right, so the first one is operating at the parameter is 700 and then 700 Celsius, and we have 6 bar, so to use that. So 6, then 700. Okay, so we can run this and then we see what we're having. Oops, we didn't add the heating source. All right, so let's add this. Can also check before I add, let's just check it and then you'll see a little bit of improvement with our hydrogen production. Let's see. So we have 0.219 mass flow of hydrogen. Okay, note this will be converted into the required products we're looking for, which is the methane, the yeah, this is going to mix up with the methane. That's the hydrogen, the formation of methane. So the carbon to also go with the formation of methane. We have the CO2 and then the CO also formed. Okay. And the ash is still the same. All right, so let's quickly add the heating source because that's why we brought this. So this is serving as a, okay, and then we run it. Okay, so after doing this, we can just add a mixer. So we combine the both products together. Then we bring this down. Okay, and then be sending this back, be sending this to another Gibbs reactor. So we have the second one. And then connect this. Our products. All right, so let's check what this is operating at. The second one is operating at 706 bar, so just make use of it. 700, sorry, 6, 700. All right, then let's just name this. Okay. So we run this. And then let's see what we have as the result. Okay, so from the results, the mass flow, we can see that we have um okay, we have carbon being formed. Our hydrogen is at 0.42, 0.421949. That's in kilogram per hour. This is what we're producing per hour. And then, okay, the carbon CO2, we have 4.5, it's quite high. CO is also 2.5. Water, let's check the methane, 0.97. Okay, so at this point, we need to separate this ash, all right, from this stream. So that we can cool it further. So let's add the second product stream to this. Okay, let's run it. All right, so with S11, you can see that the ash is being removed, and then we have the other components. This is the gaseous component. Majority of them are the gaseous form actually. Let's check on that mix to see what we really have. Okay, so this one's in vapor phases, all right, while this one is in solid. All right, this is solid here, so it's coming out. Okay, so now we need to cool this. All right, after cooling it, before we can now separate it. So we're trying to bring it down to room temperature. Let's go to add a cooler to it. Okay, we had a cooler to it. Let's go over the question so that we see some things. All right, so the step employs the decomposition of the pKs into constituent components, including carbon, hydrogen, which is the yield reactor we used. We made use of that. The combustible substance from the R Gibbs, that's the first R Gibbs, which includes the the hydrogen, CO2, um, CO, that's carbon monoxide, methane, and then sulfur oxide. So moving on, the catalyst effect was neglected. We didn't add a catalyst to it, so that's why it was neglected. And then, okay, and then was considered to operate at isothermal and isobaric conditions. So additionally, steam as a gasifying medium supplied to the bottom of the fluidized bed gasifier, where it reacts with the biomass. So our steam was like a gasifying medium, all right, for this particular process. um, the steam produced at 400 Celsius is in the superheated using the superheater using Aspen plus heater model. So that's what we did. We superheated it, and then some part of the gas is further sent for analysis. All right, so an analyzer has been used to determine the composition of the subsequent gases. So basically, after everything, you just check your results. Or that's basically what it's talking about. We're checking our results. Okay, so we have two gasifiers, which was the Gibbs 1, the Gibbs 2. All right, so the final gasification process from the Gibbs 2, okay, that's the final product coming out from the Gibbs 2. All right, so furthermore, the product stream is cooled to 25, which is what I'm trying to do now, and later we'll go to the absorption column system. All right, so basically that's the system I'm just going to use to separate our gas. All right, so a gas liquid absorber was used for the separation of liquid and gas products at atmospheric conditions. So the first thing we need to do, we need to cool it down. I'm going to cool it down, and then we bring the pressure to atmospheric condition, atm, so make it 1. And then the next thing is to Okay, a separator. Let's just make use of the two flash because we're just trying to remove the gas from the liquid. So I can name this my SYM, and then I'll just name this LIQ liquid. Okay, so coming here, put this 25 and then 1 ATM. So the process is complete. All right, so the process is complete. Let's check final results. Let's check mass flow. So you can see from this point our mass flow for, we can see that first of all we've totally converted our PKS, that's the palm kernel shell, and then we've taken it into the gaseous form for the production of the hydrogen, and then we can see we're having 0.42 of the hydrogen being produced, and then the nitrogen, we have nitrogen here, CO2 also is coming out from it. So this particular stream is actually containing majority of the syngas components, right? So we have the methane, we have the CO2, we have the hydrogen being produced. So our major concern actually is the hydrogen. We can see that we're able to get 0.42 from it. All right, so then the liquid side, we can see we're able to remove majority of the sulfur. So the sulfur wasn't actually going into the syngas stream. So basically this is just a simple process for the gasification of your palm kernel. All right, so you can optimize this, you can do a quick optimization, check what temperature will actually give more production of the hydrogen, and then do some analysis on this. All right, so we'll discuss more about this in the next class, but this is the complete setup that we need for this. So let's move this, we call this ash. All right, call the ash, and then we're good to go. We run this. So yeah, this is just a simple process for the gasification of palm kernel shell. All right, the steam served as a gasifying medium. It helps the gasification process. All right, so you can try other materials, other carbonaceous materials. All you just need to do is to look for their approximate and ultimate with sulfur content, the analysis for that. Then you put in the feed. You can just be changing the feed for it. All right, and then remember you have to first do this yield, you have to do the calculation before you can continue the process. The calculation for the yield, put into the elemental form, and then before you can continue, depending on the carbonaceous material you're using. So you can try it with other carbonaceous material, you can look for coconut shell, you can try it as well, and then get your results. So basically I just wanted you to understand how to make use of solids, how to perform a gasification process, and then how to make use of the yield reactor, the Gibbs reactor, the split unit, and then yeah, that's majority of everything that's supposed to be covered in this particular simulation. All right, so we have discussed more about this. We'll talk about the optimization of this process. That is for the students. We'll be discussing this in our class. All right, so see you all in the next class.